Well, then how do we know what kind of bond we're actually dealing with? Is there a way to predict it? Well, there is. If we use the property of electronegativity, which is something that we've discussed before. If you recall, that's the tendency of an atom in a chemical bond to attract the electrons to itself. That property will allow us to make some predictions about what sort of bond we might expect. There was a scale developed by Linus Pauling, and it's called Pauling's scale, in which he assigned values from 0 to 4, depending on the nature of the chemical element. And remember, a 4 would be something that would be very strong in attracting electrons to itself in a chemical bond, and a 0 would be one in which we would not expect to see any attraction whatsoever. Well, it turns out that there's no elements that we know of on the periodic table that have values of 0. In fact, the lowest is 0.7, and that is for the element francium. Okay, so then what we do is we say, what is the difference in electronegativity? And then once we have that difference, we can establish the bond type. So it turns out if you have a difference of 0 exactly, then that molecule is truly nonpolar covalent. That means it's an equal sharing of the electrons in that chemical bond. Now, some would argue that you can extend that to 0.4, and in fact, many people do. Even your text does. Your text describes it as mostly covalent. But we'll extend our idea of nonpolar covalency to 0.4, understanding that really the value of 0 is where you have a true molecule. So in general then, 0 to 0.4 difference, you're going to find nonpolar covalent. If you are 0.4 to 1.7, then you're going to be polar covalent, which means like in a planet like the Earth where you have North Pole and South Pole, you're going to find a molecule then has two ends, and the electrons are going to spend more time on one of the atoms than the other. The one with the higher electronegativity is the one that gets the electrons, and so that end will assume a negative charge or a partial negative charge. If you are greater than 1.7, then you're going to be mainly ionic. And a good professor of mine once said, the only molecules have a 0 difference in electronegativity, and you always will have some ionic character then. At least part of the bond will be ionic in its nature if your difference is anything more than 0. Okay, so if we apply that to lithium and fluorine, for example, remember the bond here, we're expecting an electron transfer. So the movement of the electron over to fluorine is indicative of the fact that fluorine's got a higher electronegativity. It does. The electronegativity of fluorine happens to be 3.98. Now, where am I finding that? If you would look at the back side of your periodic table, I'm just going to give you a minute to find that. And by the back side, I mean side 2. And I'm just going to zoom in here, and I'll find the element fluorine. That's about as good as I'm going to do. You can see that there's a number right up. This is side 2 in the top right corner of the box. So that applies to fluorine. That's 3.98. Okay. And then if I do the same thing for lithium over here, I can see that that's 0.98. Okay, so I have 3.98 for the fluorine, and I have 0.98 for the lithium. Therefore, the difference, we can do it as a delta, is going to be equal to 3. Applying that to our scale, we can see that that bond is mainly ionic. Now, there's something else that that table will provide us. And that is, if you look up at the very top here, you've got the percent ionic character of a single chemical bond. And if I look at that, I've got differences from, again, 0.1, because you're not going to have an ionic bond at all if you have a difference of 0. But you have a difference of 0.1 all the way up to 3.2. So then if I look at 3, I can see that the difference there of 3 provides 89% ionic character. So most of it is transfer. Now remember, that old professor, he said, bonds are never 100% ionic, never 100% covalent unless they're the same atom. So the difference between those two suggests that you do have 11% covalency there, which is kind of interesting to think about. Doing an example like hydrogen, the two atoms are identical. So if you were to look at the electronegativity for hydrogen, you find it's 2.2. Well, what's hydrogen? It's 2.2. And so the difference here is 0. So that is going to be a true molecule. It's going to be nonpolar covalent, a true covalent molecule. Now that's going to occur for 7 pairs of atoms. Do you remember what they are? You know, I think you do. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Those are the true molecules. That's how they exist at standard conditions as elemental form. And so then those will be true molecules. Everything else is going to be a combination of ionic or non-polar or polar covalency. Okay? Well, I'm going to have you take that a step further then today. There's this worksheet will be given to you, and what you see here is 15 examples, and we're going to be doing some pairings. So we've got lithium and fluorine. This X notation is the electron dot notation. So remember, for the representative elements, those are groups 1, 2, and then 3b through 8. You're going to just use the group number. So this is going to be Li with a dot, right? And then fluorine, as I've already shown you, because it's in group 7b, we'll have 7 dots. We already did the electronegativity difference. We said that was 3. We already did the percent ionic character. We said it's 89. And so we identify the bond type as mainly ionic. Okay? So you'll go through here and do examples of these. So what happens if you have something like iron or chromium or manganese? Remember, those are transition metals, and so the rules are slightly different if we look at it in full, but for right now, we can just make the assumption that it's the S and the P of the highest principal quantum number. And so for iron, being that its configuration would be argon 4s2, and what's that going to be, 3d6. Okay, so then we say, all right, we've got 2 electrons in the outer shell, because S is the highest, 4s is the highest, so we'll put 2 there. So we'll just say iron has got 2 dots. And good enough for now. And then oxygen would have 6 because it's in group 6b. Once again, you look up their electronegativity values, take the difference, put it into the chart up top for percent ionic character, and then identify it by bond type. If you can't find an exact difference, if it falls somewhere in between some of these numbers, you can interpolate, take averages, work out some kind of a formula, but if you wanted to round it to the nearest, that's fine. Okay, that would be okay. All right, I hope that helps.